Hello everyone, welcome back. So, let's check out this problem. So what do we have here? Well, we have a smooth can C that is lifted from A to B by a rotating rod. The mass of the can is 3 kilograms. Now we're going to neglect the effects of friction, most likely because this is a can and it'll be rolling. And we're not going to worry about the size of the can. So that R, the radial direction to the center of that can, is going to be 1.2 cosine of theta. Now what you want to find is the force of the rod on the can when theta is equal to 30 degrees. And when our radial angular velocity is 0.5 radians per second, which will be constant. So, I'll let you do this on your own as usual, and I will send you off to try it. So how are you going to do it? Well, you're going to find the acceleration component using the kinematic equations. You're going to draw a free body diagram and kinetic diagram, and then you're going to apply the equations of motions to solve for the forces. So, go forth, try it, and tell me how you do. Now, 3, 2, 1, and we're done. So you came back, you paused, you did it. It went terribly. But you came back anyway because you want to figure out how it's done. Glad you're here. Let's get to work. First off, we know what the radial position is, and so we can see how that changes with time. And we're using the chain rule to get this, where we don't know what dr dt is, but we do know d theta dr d. Make sure I do this right, because I always want to mess things up. Nope, I did it wrong. I always did it wrong. dr d theta dt is the same exact thing. So we take our derivative with respect to theta, and then we multiply everything by our time derivative theta, which is our angular velocity, which luckily for us is constant. Now we know all this. It was given to us. We know that theta is equal to 30 degrees. We know that our angular velocity is constant is 0.5, and therefore angular acceleration is 0. And so we can get the radius and how quickly it's changing as well. And then from that, we can plug it into our acceleration equations to know what the radial and transverse components of acceleration are. Okay, now we need a free body diagram to help us out. So we know that there is a weight pressing down. And that will be the mass, which is 3 times 9.81. There's a normal force, which is resisting that and pushing back up. And there is just a force of our rod pressing on the can. That's going to cause acceleration in the transverse and radial directions. So now by summing along our radial and transverse directions, we can get that our normal force is 15.2 newtons and our force of the rod on the can is 17 newtons. And we're just doing this by breaking everything up into components. Now, when you look at this right here, that is just saying that is newtons, not that that is a function of the normal force. It's hard when we use these same exact symbols for various different parts of the problem. And then right here, you see the components of our acceleration that we solved earlier. So I think that's it. Yes, it is. So thank you for listening. I hope this helps you, and I will see you all next time. Bye-bye.